Today, we're honored to be welcomed by Professor Karen Livescu, one of the foremost researchers in speech and language processing. She is a professor at the Toyota Technological Institute at Chicago, as well as a courtesy appointment in computer science at the University of Chicago. And in today's episode, we'll dig deeper into how Karen thinks about representation learning in speech and how her lab right now is pushing the horizon in natural language processing. Thank you so much for your time, Professor Livescu. Let's first begin by talking a little bit about what your lab is doing right now when it comes to artificial intelligence and exploring how you can push the boundaries with language processing.
Sure. And thanks a lot for having me, first of all. So my group works on all modalities of language. So that includes spoken language, written language, and even sign language. So we deal with audio, we deal with text, and we deal with video. And I would say that the sorts of things that we're doing have to do with making language, models of language, not necessarily language models, but models of language more universal. So that means that a single model can do more things, or a single model can work for more users. For users of more languages, more accents, and so on. And what that means is for a lot of different sorts of languages, accents, and so on, there's a lot less data available than there is for, say, the majority languages like English and the major European languages and Chinese. And so a lot of what we do is focusing on how can we automatically learn models using less data. So I'll start there, and then I'm happy to expand on whatever you would like me to.
Yeah, I was interested in some of the techniques the lab is exploring right now when it comes to learning languages really fast with the way less data. I've come across terms like maybe representation learning, but I'm not really sure how those processes work necessarily. So if you could go more in depth, that'd be really helpful to help me understand.
Yeah, absolutely. So let me start by saying what representation learning is. So as you probably know, a lot of the systems that we use today in AI are based on deep networks. These are deep neural networks with lots and lots of parameters. So they're basically just a very, very complex function. So, it might be approximated by a polynomial with a whole bunch of polynomial terms, or it might be some even more complex function, but at any rate, it will be characterized by a bunch of parameters. And the idea of representation learning is the model can be thought of as first computing some kind of representation of whatever the input is, and that representation might be a vector or a set of vectors or a very, very long sequence of vectors, and then doing something fairly simple to that representation. So a lot of the work in these models is shoved into the representation, how we compute that representation. So one idea, which has been very effective, is to try to learn representations from a whole bunch of data that isn't labeled or annotated in any way, just raw, unlabeled data. And it might seem magical if you haven't seen this idea at work, but it really does work. We can learn to represent the important bits of information in, let's say, a speech waveform. And those important bits of information might be things like the pitch of your voice, what frequencies are more represented or less represented, which ones are more represented at a particular point in time than another. But all of this, these are things that are kind of intuitive, but all of these things are actually learned automatically by a model from a whole bunch of data. And then the idea is once we have these representations that are very, very general representations of speech or of text, then we can learn very simple models using just a very small amount of labeled data to do whatever task we want to do, whether it's speech recognition or translation or summarization or whatever. And that's how we get away with using less labeled data or less data from the specific language or setting that we want, if that makes sense.
When it comes to using less data, how much less data do these techniques necessarily need?
So let's see. So in a recent project of ours where we were learning speech recognition for a whole bunch of languages at once, multilingual speech recognition, we used representation models that were trained on hundreds of thousands of hours of speech in hundreds or thousands of languages. And then we would use just 1 hour of recorded speech in some low resource language where we only have say that much transcribed speech, and just learn a little bit, a few extra parameters using that 1 hour of speech from the low resource language.
And when it came to the accuracy of the model on maybe new parts of the language, how did that representation model perform?
Right, so how did it do on a new language that it, let's say, hadn't seen before, and we only got an hour of labeled speech? So we're not doing nearly as well on these low resource languages as we are on high resource languages, but we can improve performance from, say, completely unusable on some of these languages to kind of usable, so you can kind of get the gist. And for some purposes, that's really enough. For some purposes, you might just need to figure out what is the topic of the conversation or something like that. And for that purpose, it's enough. But this is research. This is really bleeding edge research. So these are not solved problems. We might have improved performance by some delta that we're very, very excited about, but it doesn't mean the problem is solved, and that's why we still have work to do.
When it comes to using representation learning, has any company started adopting it in order to increase the language support that their product is able to provide?
Yes. In fact, there's a lot of cross-pollination these days between academic research in universities like ours and industry research groups. And so, for example, in the research that I just described to you, we used some representation models that were actually trained by industry groups, by Google and by Meta. And they're the ones who tend to have the really, really large amounts of computing resources. And so a lot of times an idea will maybe be born in an academic group, but we can't really scale it up to the same level that an industry group can. And then they'll take that idea, scale it way up, produce an even stronger model that we can then use to do the kinds of experiments that I just described.
Makes a lot of sense. And just to backtrack a little bit, because we've been talking about a lot of the work the lab has been doing right now when it comes to using deep learning in order to process a lot of low resource languages, where was the lab, let's say, a decade ago? And how has progress changed since then?
Good question. So a decade ago, this would be 2015. So this was still fairly early in the deep learning revolution. So it was around 2012 or 2013 when I think the research community became convinced that deep learning is where we're all going, at least for speech. And also for other modalities, but certainly for speech. And so at that point, around 10 years ago, people were still studying different sorts of models. So if you've heard of things like, feed-forward networks versus recursive neural networks versus transformers, these are all different architectures, different forms of these deep functions. And at the time, that was a very active area of research. It's not inactive right now, but there's a lot more agreement now on what types of models we're all using, whereas at the time there was a lot more kind of exploration of the design space. And I think the really big thing that's happened in the last few years, of course, is all these large language models like ChatGPT and Gemini and so on. And along with those, really large representation models is also a fairly new thing. So what does that mean for what our capabilities are? That means that we can do a lot more with a single model. So now we can have the same model identify a language, recognize the words in that language, translate between that language and some other language, all in one model. And that wasn't something that anybody dreamed about 10 years ago. 10 years ago, we were still, just improving one single speech recognizer or one single language identification system. And so that's been a huge change in the field.
That's really interesting. One thing I've heard from other people in the field is like the bitter lesson and how these models have architecturally gotten a lot simpler rather than getting more complex. Has that same phenomenon been like a big thing in speech recognition as well as other language processing work as well?
Definitely. So I would say that, while we used to try to think of very clever ideas based on our knowledge of how human speech works, either human speech understanding or human speech production or our language facility. Nowadays, there's a lot less of that. There's a lot more just collecting as much data as you can get, scaling up the models as much as you can, collecting all of the compute hardware that you can get, and that's sort of what the bitter lesson taught us to do. But there is a caveat, and I want to make this point, that I don't think that cleverness has gone away. It's not that now we can replace all of our cleverness and all of our ideas and all of our creativity with data. I suppose if we had infinite data and we had infinite compute, then we could. But we're reaching the limits where, modern language models have been trained on essentially all of the text that has ever been produced, and speech recognition models are trained on essentially all of the speech that we could possibly train them on. And still we don't have enough data for some languages, and we don't have enough data to do well on certain things. So in my view, this is where we need to start employing our creativity again. And so I think we'll start to see again some more sort of interesting innovations that go beyond just scaling up the data. And you might get different answers to that question depending on who you ask, but that's my view.
Are there any interesting directions you're seeing right now beyond just scaling?
Definitely. So let's see. I could mention two things along these lines. One of them goes back to the multilingual speech recognition example that we already talked about. So when we talk about multilingual speech recognition, there are 7,000 languages in the world. But those languages aren't just a collection of random languages. They're actually structured. Some languages are related to each other, so you probably know that they're language families. There's Romance languages and other types of languages, and we can use information about which languages are related to which other languages to help us decide which language's data will be most helpful for learning a model for some other language. And that's a place where having a little bit of knowledge of linguistics and a little bit of knowledge about language history and language classification is really helpful. So that's one example. Another example that I want to mention is, like I said, my group works on all modalities of language. And one modality of language, sign language, the research is much less developed for sign language than it is for spoken and written language. And there's a lot less data for sign languages. There's a couple of hundred sign languages in the world, and there's a lot less data for any of them. And so what are the clever things that we can do there? Well, one of the things that we know about sign languages is that in order to speak or to sign in a sign language, you combine information from your hand motions, your arm motions, your facial gestures. And so in our work on sign language, we use this fact, since we can't just ingest a whole bunch of video and learn a giant model on the raw video because we just don't have enough data to do that, then we have to be a little bit clever. We look for just those bits of information where the hands are, where the body pose sits, where the facial gestures are, and then we learn representations for those parts of the video. And that's something that, again, we need a sign language linguist to tell us what to look for, and to use a little bit of cleverness to not just have this one simple model, but rather combining all of these streams of information.
I want to move on to talking a little bit more about you and your background and how you got into artificial intelligence. So I know you first started off with a bachelor degree in physics from Princeton. So I was just interested, how did you go from doing physics into getting into language processing and artificial intelligence, especially before deep learning was really a big thing?
Yeah. So maybe to explain that, I should backtrack even a little bit more to high school. And when I was in high school, I really just loved math. And I thought that I would be a mathematician, and I would go to college and I would major in math, and that would be my life. And I really didn't think about anything else. And then when I got to college, I didn't like my math classes nearly as well as I thought I would. I didn't do as well in them as I thought I would. I don't know if it was a coincidence or, something about what college math is like versus high school math. But whatever it was, I started looking around for other majors. And like I said, I really hadn't thought about anything else until that point. So I just looked at like the next closest thing, which to me was physics, and did that. But it wasn't something that I particularly loved. I didn't get into it because I loved it, just because I needed another major. And so the whole time that I was majoring in physics, I was actually kind of looking around at different things as well. So I did a minor. They don't call it a minor at Princeton. They call it a certificate program. So I did a certificate program in linguistics and cognitive science because that looked interesting. And then I did, and became very interested in language as a result of that. I did a summer internship at Bell Labs, which was a research lab, still is a research lab, but at the time was very, very large. And I did a summer internship on speech synthesis, and that really hooked me. And at that point, I decided that I was going to do something related to that in grad school. And then after my undergrad, I took a year just to catch up on computer science classes and electrical engineering classes, and then went to grad school in a speech group. So that was how I got into that.
After grad school, was the immediate thought to get back into academia, or did you have a few years that you spent in industry working on products?
I never worked full-time in industry. I had internships throughout my studies. But after grad school, I applied for both industry jobs and postdocs. And of the offers that I got, I just thought the postdoc seemed the most interesting. So I ended up taking that. After my postdoc, I applied for both faculty positions and industry positions, and I got a nice faculty job. And I figured at the time that it's easier to go from academia into industry than the other way around. So I thought that as long as I had an appealing academic offer, and as long as I was enjoying myself, I would just stay in academia until I didn't like it anymore. And I've just never not liked it anymore. So here I am.
That was pretty interesting, going from really liking math to jumping into physics and then speech recognition. I think it resonates a lot with a lot of Hack Clubbers who have a lot of interests and are trying to find what they want to do. I want to move more into some questions that maybe Hack Clubbers might be more interested in, particularly maybe some open problems you might have in the back of your mind in speech recognition, some like maybe puzzles that people in the audience could think about that you're actively thinking about right now as well, and that maybe is a little bit more entry level to keep people engaged.
Sure. So I don't know if this is entry level. It's hard to be both entry level and something that we're thinking about right now. But this goes back to, data size and model size. So probably all you guys are using ChatGPT or the like. And these are very, very large models. In order to train them, like I mentioned before, we need ridiculous amounts of data, essentially everything that's ever been written. We need many millions of dollars that these companies are not quite telling us how many hours of compute on really large numbers of GPUs and really large amounts of electricity. And really large amounts of water for cooling all those GPUs. And it's a very, very resource intensive thing. And this is where the world is going, right? We're basically in the middle of an industrial revolution where these models are a new technology that's taking over how we do many things. And so the more that we rely on these models, the more that we sort of become slaves to this hunger that they have for resources, for electricity, for data, for water, and so on. So one of the things that keeps me up at night is how can we make these models not consume so many resources? And that's, related to the problem we talked about before about training models when we don't have a lot of data, but from a different angle. The angle here is just how can we not be so wasteful? Why do I think that this is possible? What makes me think that we could have smaller models? Well, humans learn language, learn to speak, learn to do all of the things that we do and all of the things that AI is now taking over. We learn to do those things with a lot less data and a lot less energy than ChatGPT does. So we're sort of a proof of concept that this is possible. And so a big puzzle for me is how do we build models that can do that can be as efficient as humans are. And I don't know what the solution will be. Maybe we'll have to understand a lot better what humans do and be clever. like we were talking about before. Or maybe there'll be some clever computational trick, an optimization of all of the algorithms that we use that will allow us to be a lot more efficient. And even if you don't care a lot about wastefulness or don't care a lot about the environment, you probably care about, having these models available to you on your little tiny device, which right now we can't have. So if you, for example, want to have a model that is private to you, so you don't send all of your private data to OpenAI or to Google. What you'd really like is a model that just lives on your device, that's that small, and that you can train really quickly on data that you care about. And that just doesn't exist right now. So that's a big puzzle.
Have you seen any biologically inspired work? Maybe tapping into that analogy you were talking about with the brain being a lot smaller, that's able to potentially get somewhere close to how models are right now?
I would say that some of the models that we use are biologically inspired. So none of them look exactly like what our brains or bodies do. But I think just based on knowledge of the developers of these models and the process by which they were developed, I know that they were thinking about, hey, how does the brain work? Well, way back when deep learning models were invented, even before they were deep, just neural models, the model was the human brain. Hey, we have these neurons, they're densely connected, but each one of them executes only a very, very simple function. So maybe we can collect a whole bunch of these neuron-like things, each of which does a very simple function, and turn that into something very, very complex and powerful. And that really came from a biological inspiration. And then other types of models, like convolutional networks, came from some amount of understanding of how the human, especially visual system, works. And some other models I'm less kind of aware of how they came about, but I believe that there's often been this little bit of inspiration where it's not that the models look exactly like anything in our brains, but that people who understand something about how our brain works, that knowledge helped them to develop these models. There are models that try to a lot more faithfully represent what's in our brains, and they tend not to be sort of the mainstream successful models, and they're used more for modeling humans and for scientific purposes.
I know one strand of research right now that is pretty popular is interpretability work, and trying to be able to dissect what's going on inside of models. Have you seen any interesting results from that strain of research, and any way that might inspire future models to be more efficient?
Yes. And in fact, my group did some of the early work on interpretation of speech models. There had been a lot of work before that on interpretation of text models and interpretation of visual models, and we did some of the earlier work trying to figure out, which layers of a representation model correspond to which property of speech. And so we did things like find that certain layers had more to do with speech sounds, phonemes, consonants, vowels. Some layers had more to do with words. Some layers had more to do with low-level acoustic information. And that's sort of one type of interpretability work where we have a model and we try to figure out, kind of go under the hood and figure out what it knows and where in the model different bits of knowledge live. Other types of interpretability work are trying to get the model to be inherently interpretable, to kind of explain itself to the user. If you're going to diagnose somebody's X-ray as having some illness, the model should be able to explain, in a way that a human understands, what about that X-ray makes it think that the person has that illness. So those are kind of two slightly different forms of interpretability, and I think they're both very, very important. And you asked, how might that help us to build better models or to be more efficient? And a lot of times this interpretability work is very exploratory, and we kind of have no idea what it will lead to. And it's usually interesting, and it satisfies our scientific curiosity before we get anything practical out of it. But then sometimes we get something really practical out of it. So, for example, in our own work, when we notice that For example, the layers of a model that learn the most linguistically meaningful information tend to be not the highest layers of a model, not the deepest layers of a model, but some intermediate layer. And that told us that, well, maybe we could get rid of the last couple of layers, or maybe before we use them for any task like speech recognition, we should we should forget the parameters of those layers and relearn them. And that was something that, we hadn't thought of until we did that interpretability work. So I think it's those kinds of things that we get out of this.
For this last segment of the AMA, I wanted to pivot more towards other areas in which AI is used besides just language processing. One thing I've been reading recently and been looking a lot into recently is protein language models, and how there's a lot of overlap between protein structures and sequences, as well as how we use models that model natural language. And I was just wondering, is there any overlap with the stuff your lab is doing with representation learning that could be cross-applicable maybe to protein language models? And if so, how?
Right. So at a very basic level, a lot of the models that people are using across all of these domains, anything that involves sequences and anything that involves things that aren't even a sequence but that we can turn into a sequence, like we can take an image and use raster scan order to read off the pixels in an image, if you know what I mean, and then we've turned the image into a sequence of pixels. So people love sequences these days because we have these great language models for modeling sequences. Anything that looks like a sequence, we can then apply essentially the same model to. And so I don't know what to say beyond that in terms of parallels, other than to say, everything that we've learned from modeling sequences of text, sequences of speech, along the way we've learned lots of things about how do we, when we're training these models, we're trying to optimize some measure of goodness. What are the useful ways of optimizing it so that it can learn to model really long sequences, so that it can learn to model data in a really, really high dimensional space. And all of these things are just very general questions. They came up first maybe in modeling text or first in modeling speech, but they also apply to protein sequences, which are very, very long. And if there are techniques that have to do with learning from less data, well, protein sequences are a great place where we don't have a whole lot of data. There's only so many proteins, so many sequences that have been labeled in a particular way. So any technique there will naturally apply over to protein sequences. There are some things that are not going to apply. I don't think we have the same type of hierarchical grammar of proteins that we have for language. There's some sort of grammar, sort of structure of proteins, but it's not the same. So there's some things that are not going to transfer over, but many, many techniques do.
One thing that I was reading about recently that I think has a little bit of overlap with representation learning was this paper, and I forgot who wrote it, but they trained a sparse autoencoder on a protein language model, and they were able to basically get a lot of features in the model that corresponded to biologically relevant concepts, and then they were able to use that sparse autoencoder to label a bunch of data. So that was one very practical use. And I was wondering, is that similar to how these representation learning methods are done in order to very quickly get up to pace with a new language?
So sparse autoencoders specifically have not been as widely used in language models or models of speech. They've kind of made an appearance, but they have not been used in the way that you're describing. Really, the main way that representation models are used is just to learn useful features. Like if I give you, a raw piece of audio, just a raw waveform. Have you ever looked at kind of a raw audio waveform? And so you know that it's very, very complex looking. But so then extracting out of that something like, where are the consonants? Where are the vowels? That boils down to representation learning, to figuring out what patterns in that waveform correspond to consonant likeness or vowel likeness. And so that's the more common use for representation learning, is just learning features. And then those features can be used with a lot less data to learn to do something useful.
And with the representation learning, the features you were extracted are like a limited set that's like pre-coded. For example, like it has to be a constant or it has to be a vowel.
So no, it's not pre-coded. Really what we usually pre-specify is just what is the form of the model, what is the form of the function that we're going to learn, and what is the dimensionality of this vector of features that we're going to learn. Stop me if I say anything that I should be defining, by the way, because I don't know what everybody's background is here. But yeah, so usually we only specify these very, very simple things, and then the models learn on their own. Right now, if you took 10 milliseconds of my speech, the model might produce a vector that describes those 10 milliseconds. And part of that vector, which might be like 1,000 dimensions, part of that vector would encode something about the pitch of my voice, part of it would encode vowel and consonant properties, but we don't know which part. And that's where interpretability work comes in. And sparse autoencoders, like you were mentioning, one of the nice things about them is that they're easier to interpret, that they give you just a small number of features to look at. Whereas a lot of representation learning methods just give you this gigantic vector, and it's up to you to figure out, if you want, what is the meaning of the elements of that vector.
So it seems like using or like finding what direction a certain feature you want in this very high dimensional vector, that type of method appears at face value to be a little bit more precise than using a sparse autoencoder. But using a sparse autoencoder probably reduces accuracy, but at the same time, maybe it's easier to interpret. Yeah, those are my...
So when you talk about the representation being more precise, you're thinking about just the fact that it's higher dimensional.
Yeah.
And so presumably it can encode more information. And I think that's true. The higher the dimensionality that we represent a signal as, or some data as, the more information we retain. But it's very context dependent, what information you really care about. If you really just care about a few things for your purposes, then you want that model to really just pinpoint those few things. Like when we do speech recognition, our goal is to go from a speech waveform to text. We don't care about who spoke that text or what accent they have or what mood they were in and what emotion they were expressing with their speech. So we don't need a model that encodes all of that information in some giant vector. Perhaps we would prefer a sparse autoencoder that just pinpointed the things that we need. The main reason that we use these giant models with giant representations is that we often don't know exactly what we're going to need ahead of time. And so if we have enough data to learn a big model to do all of these things at once, then we do.
That makes a lot of sense. As we approach the end of this AMA, I just want to thank you for joining us today and spending your time today talking about the work your lab is doing, the stuff when it comes to representation learning on low resource languages, making language models more accessible, speech recognition more accessible. And yeah, just thank you so much for sharing your time and talking about all the work you've been doing.
Thank you for having me. It's been my pleasure, and thank you for all of the excellent questions.